So you build a massive, like 70 billion parameter intelligence.
Huge undertaking, yeah.
Right. You train it on these giant clusters of GPUs for months. And, it can write complex Python scripts. It can synthesize historical documents. It can even reason through multi-step logic puzzle.
The cutting edge of what's possible.
Exactly. So you deploy it. A user logs into your brand new application. They type hello and they hit enter. And then just a spinning wheel.
Oh, the dreaded spinning wheel.
1 second passes. 2 seconds. The user pulls out their phone, they switch to another tab, and the session is just dead.
Yeah, they're gone.
The intelligence of your model completely ceases to matter because the actual physical physics of your deployment just failed.
It's a brutal reality check.
It really is. And we have a highly technical stack of notes today. We're talking benchmarks, hardware profiles, deployment white papers. Our mission for this deep dive is to unpack the raw, unforgiving physics of making AI fast.
Right, getting into the weeds of it.
We are looking at latency, throughput, and the severe physical bottlenecks of silicon.
Okay, let's unpack this because, you can have the most robust hallucination-free model on the market, but if it takes 10 seconds to type its first word, your application is already obsolete.
Yeah, the gap between a theoretical model running in a research lab and a production system serving, say, thousands of concurrent users, that gap is entirely defined by those physical constraints.
It's totally different math.
Exactly. When a user abandons a session because of a loading spinner, they aren't rejecting the quality of the neural network, they are rejecting the latency.
Right.
The engineering challenge is that large language models are inherently heavy. I mean, moving massive amounts of data to generate a response, it creates inevitable friction.
But before we look at what the GPUs are actually doing on the back end, we need to look at the psychology of the person sitting at the keyboard. The sources highlight one metric above everything else when it comes to the user's perception of speed.
Yeah, that crucial metric.
Time to first token. TTFT. Right. Time to first token is the absolute time elapsed from the exact moment the user hits enter on their prompt to the moment the very first piece of the response appears on their screen.
Just that first little flicker of text.
Exactly. And what's fascinating here is how this single metric dictates the perception of the entire system, regardless of the overall generation time.
Wait, really? The overall time doesn't matter as much?
Not initially, no. Human attention spans degrade exponentially after about 400 milliseconds of dead time.
Wow. 400 milliseconds.
Yeah, it's fast. If nothing happens on screen within that window, the user's brain registers the system as broken or at least sluggish.
It's like being at a restaurant. You sit down, you look at the menu, and you place your order.
Okay.
If the waiter brings you a glass of water and a bread basket immediately,
Yeah.
you feel attended to.
You're in the system.
Right. You know the kitchen has received your order. You really don't mind that the steak takes 30 minutes to cook because you're engaged. You're snacking.
That's a great way to put it.
In the context of building AI applications, streaming that first token to the UI is the digital breadbasket.
It absolutely is. Implementing streaming, which is sending tokens to the client asynchronously as they're generated, rather than waiting for the entire response to compile, it's basically a psychological hack.
A total trick on the brain.
Yeah. Consider a model that takes 5 seconds to generate a complete paragraph. If you batch that response, the user waits 5 seconds in total silence.
Which feels like a lifetime in software.
It really does.
Yeah.
But if you stream and that first token arrives in a few hundred milliseconds, the user starts reading. The cognitive load shifts from waiting to processing information.
And suddenly the system feels instantaneous.
Exactly.
I want you, the listener, to think about the products you're building right now. Are you making your users wait for the steak in an empty room? Or are you dropping that breadbasket immediately?
It's an important question.
Because the perceived difference is massive. But this brings up a stark reality. We drop the breadbasket, we get that first token out fast. Why is the rest of the generation so slow? Like, what is physically happening on the server that makes writing out a paragraph take so much longer than reading the prompt?
Well, to answer that, we have to transition from user psychology to the literal architecture of the hardware.
Okay, let's get into the silicon.
An LLM's workload is split into two fundamentally different phases. You have the prefill phase and the decode phase.
Prefill and decode, got it.
And these two phases are bottlenecked by entirely different physical limitations on the chip. The prefill phase happens first.
Right.
This is when the model receives your prompt. Let's say it's a massive block of code you want debugged. The model processes all of those tokens simultaneously to establish context,
Okay.
and this phase is entirely compute-bound.
Meaning it's limited by the actual number crunching power of the GPU's compute cores. Like, it's just doing math.
Exactly. Massive parallel matrix multiplications. The GPU reads the weights of the model and applies them to a huge chunk of text all at once.
Because all the input data is right there.
Yeah. Because the input is a large batch of data, the compute cores are fully saturated. They're doing floating-point operations as fast as the silicon allows.
So the bottleneck is literally just the speed of the processors themselves.
Right. But then the prefill phase finishes, the context is understood, and we output that first token.
We drop the breadbasket.
We drop the breadbasket. Now we shift into the decode phase. This is where the model generates the response, token by token.
And the sources point out this phase is not compute bound anymore, right?
Not at all. It is memory bandwidth bound.
Memory bandwidth bound. Okay,
Nope.
Unpack that.
This is the hidden trap of AI performance. During the decode phase, to generate one single token, the GPU has to load the entire neural network, all the billions of weights from its memory, its VRAM, into the compute cores.
Just for one word.
Just for one word, it does a tiny fraction of math to predict the next word, and then it has to do the entire memory transfer all over again for the next word.
Wait. I need to make sure I'm understanding the physics here. For the decode phase, the GPU isn't struggling with the math.
No, the math is easy.
So the compute cores are just sitting around idling, waiting for the data to be fetched from the chip's own memory.
Yes, exactly. You have incredibly powerful compute cores basically starving for data. The pipe connecting the GPU's memory to its compute cores simply isn't wide enough to feed the data fast enough for token-by-token generation.
Oh, wow. So it's like having a warehouse full of encyclopedias that's the VRAM.
Right.
And in the next room, you have a million genius scholars, the compute cores. But the only way to get the books to the scholars is through a single rusted turnstile.
That's a perfect analogy.
The scholars aren't slow. They could read the books in a microsecond. But they're just standing around waiting for the books to squeeze through that physical turnstile.
And that turnstile is your memory bandwidth. When we talk about a GPU having, say, 2 terabytes per second of memory bandwidth, that sounds massive.
Yeah, it sounds like plenty.
But when you are moving a 140 gigabyte model across that bus for every single word generated, that turnstile becomes a severe physical bottleneck.
Right. And if the memory bandwidth is a physical soldered pipe on the motherboard, I can't make that pipe wider without buying a new generation of hardware.
You're physically stuck.
So I'm stuck. As a software engineer, my immediate reaction is, how do we cheat this system? We can't change the hardware physics. There has to be an algorithmic bypass.
And there is. The engineering community developed a brilliant workaround called speculative decoding.
Speculative decoding?
Yes, it directly attacks the problem of idling compute cores. The sources indicate it delivers a 2x to 3x latency improvement.
Yeah, okay, let me stop you right there. A 3x speed up in engineering usually comes with a massive catch.
Usually, yeah.
You don't get huge latency reductions for free. Usually you sacrifice accuracy. But the notes say there's absolutely zero quality loss.
Zero.
How does a software hack bypass a physical memory bottleneck without degrading the output?
By using a smaller model to run interference. Speculative decoding introduces a second, much smaller neural network into the architecture. We call this the draft model.
Okay, a draft model.
Because this draft model is tiny, maybe a few 100 million parameters instead of 70 billion, its memory footprint is negligible. It easily fits through the turnstile.
So it's fast.
Very fast. It races ahead and quickly generates a sequence of, say, 5 predicted tokens.
But it's a tiny model. Its predictions are going to be lower quality, right?
Right.
It might hallucinate or choose suboptimal words.
Sure, but it acts purely as a rough draft. It takes those 5 predicted tokens and hands them to the massive, high-quality target model.
The scholars.
The scholars. Now, recall the mechanics of the prefill phase. The massive model is incredibly efficient at processing chunks of text all at once in parallel.
Right, because it's compute bound at that point.
Exactly. It takes those 5 draft tokens and it verifies all of them in a single, massive, parallel forward pass.
Okay, here's where it gets really interesting. Let me put this in terms every software engineer listening will immediately recognize.
Go for it.
This is a brilliant, over-caffeinated intern.
Ha! Yeah.
The intern is the draft model. They rapidly type out a 5-line chunk of boilerplate code. The intern is fast, but, sloppy.
Makes mistakes.
Right. Then, the senior engineer, the massive large language model, glances at the screen. The senior engineer can read and approve that entire 5-line block of code instantly.
Just quick review.
Exactly. And that is vastly faster than forcing the senior engineer to slowly type out that exact same code, character by character.
And the physics of the GPU make this possible. For the massive model, doing a forward pass to verify 5 tokens takes almost the exact same amount of time as doing a forward pass to generate 1 token.
Because the turnstile is the bottleneck. You have to load all the books from the warehouse anyway.
Exactly.
While the books are in the scholar's hands, they might as well verify 5 words instead of just 1.
You nailed it. If the massive model agrees with the intern's draft, you just outputted 5 tokens in the time it usually takes to output 1. You get a massive speed multiplier.
But what if the intern makes a mistake?
If the massive model disagrees with the 3rd token, for example, it rejects it, corrects it, discards tokens 4 and 5, and you start the process over from the correction.
I see.
But because the large target model has the absolute final say on every single token, the mathematical output is identical to what the large model would have produced on its own.
So, zero degradation in quality.
0.
Using idle compute to offset a physical memory bottleneck? That is so smart. But speculative decoding feels like an end run around the turnstile.
It is a clever workaround, yeah.
Right. It masks the problem. Is there a way to attack the turnstile directly? If the problem is moving 140 gigabytes of data from the VRAM to the compute cores, can we just make the data itself lighter?
Yes, we can compress the model itself. This brings us to quantization, specifically to INT8. It is the most impactful data compression technique in modern deployment.
Okay, so usually neural network weights are stored as floating point numbers, right? Like high-precision 16-bit or 32-bit floats.
Right. And they contain a lot of decimal precision, which takes up physical space in memory. Quantization is the process of compressing those weights from high-precision floats into lower-precision 8-bit integers, INT8.
So you're basically halving the physical size of the data.
You cut the memory footprint of the entire model in half. You can fit a larger model on a cheaper GPU.
Which is great for cost.
Absolutely. But more importantly for latency, because the data is half the size, you can shove twice as much of it through that turnstile in the same amount of time.
Oh, wow.
You proportionally increase your token generation speed simply by changing the data type.
Wait. I have to push back on the math here.
Sure. What's the issue?
If I'm building a physics engine for a video game, and I round off the number pi from 3.14159 to just 3, my rocket ship misses its orbit and crashes.
Definitely.
Right. So if you take a neural network with 70 billion delicate, mathematically tuned weights, and you aggressively round them all off into clunky 8-bit integers, how does the model not turn into a massive hallucination engine?
It seems counterintuitive, I know.
The notes claim this is a free quality optimization. How does losing half your precision not destroy the intelligence?
It's because the architecture of large language models makes them remarkably resilient to precision loss. Neural networks are wildly over-parameterized.
Meaning there's redundancy.
Massive redundancy. You don't have one single weight determining a complex fact. You have millions of weights acting together as a probability distribution.
Okay.
When you quantize to INT8, you are introducing rounding errors, yes, but because you have billions of parameters, the positive rounding errors and the negative rounding errors tend to statistically cancel each other out across the layers of the network.
Oh, that is fascinating.
The consensus of the network remains intact.
So the intelligence isn't stored in the microscopic decimal points. It's stored in the macro patterns of the billions of connections.
Exactly. And the empirical data proves this. For almost all production use cases, the difference in output quality between a 16-bit float model and a properly quantized INT8 model is statistically indistinguishable to the end user.
So it's basically the exact same model behavior.
The model still writes the same code. It still extracts the same entities. The sources advocate strongly that INT8 quantization should not be viewed as an exotic, experimental optimization.
Standard.
It must be the default for production serving. If you deploy an LLM today and you are serving it in 16-bit float, you are basically burning money on unnecessary GPU instances and delivering a slower product for no tangible gain in intelligence.
Okay, so we manipulate the user's perception with time to first token.
Right.
We bypass the idling compute bottleneck with speculative decoding.
Yep.
We physically shrink the data with INT8 quantization to shove it through the memory bandwidth faster. We are wringing every ounce of speed out of the silicon.
Pushing it to the absolute limit.
But the sources suggest we need to look beyond just a single model running on a single GPU.
Right. If we connect this to the bigger picture, Optimizing one massive model is really only half of the production equation.
What's the other half?
Is system architecture. The ultimate cost-latency trade-off isn't solved inside the VRAM. It is solved at the network layer in how you route your traffic. The sources detail what they call the portfolio approach.
Meaning you don't treat every user query like it requires a supercomputer.
Exactly. The most expensive mistake in AI deployment is treating all prompts as equal.
Yeah, that makes sense.
Some queries are incredibly simple. Extract the zip code from this text or summarize this 3-line email. Other queries are highly complex. Debug this nested asynchronous loop or write a legal contract based on these 50 constraints.
Totally different workloads.
Right. If you use a massive, highly capable but heavy and slow model for the simple queries, you are wasting compute and punishing the user with unnecessary latency.
But this is where I struggle with the implementation. If a user is just typing into a single text box on my UI, how does the system know?
Know what kind of query it is.
Yeah. How does a routing layer know if a query is a simple entity extraction or a complex logic puzzle before it actually runs the model?
You can't ask the big model to check the complexity because then you've already incurred the latency penalty.
That's where you build a semantic router.
Semantic router.
Yes. This sits in front of your LLMs. When a prompt comes in, the router doesn't generate text, it analyzes the intent. Often it converts the prompt into a vector, embedding basically a mathematical representation of the prompt's meaning, and checks its distance against known clusters of hard or easy queries.
Oh, so it mathematically maps out how hard the prompt looks.
Right, or it uses a lightning-fast, ultra-tiny classifier model whose sole job is to flag complexity.
So the router looks at the math of the prompt and says, oh, this is just a simple data extraction task. Wrote this to the 8 billion parameter model. It will answer in 50 milliseconds.
Exactly. And if the router sees a dense, multi-layered logic problem, it acts as a gatekeeper and says, this requires deep reasoning.
Yeah.
Wake up the 70 billion parameter model. The user will have to wait, but they need the accuracy.
Wow.
Okay.
And you pair this with a caching layer. If a user asks a question that has been asked 1,000 times before, you don't hit a model at all. You serve the answer from the cache instantly.
You know, this really strips the mystique away from AI. This is just standard systems architecture.
It really is.
You wouldn't spin up your heaviest, most complex database cluster just to serve a static profile image on a web page.
Of course not.
You'd use a content delivery network. So why use a massive LLM to answer a basic routing query? You build a portfolio. Lightning-fast tools for easy jobs, heavy tools for hard jobs.
Applying traditional architectural discipline to neural networks is what defines a mature deployment. You have to stop treating the model as a magic black box and start treating it as an extremely expensive, highly constrained microservice.
We've covered the physics of that microservice extensively today. We started by recognizing that user perception is governed by time to first token.
The digital breadbasket.
Yes. You have to drop that breadbasket to keep the human brain engaged while the system works. We broke down the dual nature of generation, learning that while processing the prompt is compute-bound, generating the response token by token is severely bottlenecked by the physical speed of the memory turnstile.
The VRAM transfer.
Exactly. We explored how software engineering fights back, using speculative decoding to let a fast intern model guess the answers so the senior model can verify them in parallel, utilizing those idling compute cores.
Such a brilliant hack.
Truly. We address the math of shrinking the data itself with INT8 quantization, absorbing rounding errors across billions of parameters to double our throughput. And finally, we zoomed out to see that true scale comes from a portfolio architecture, semantically routing tasks to the right size tool before the heavy lifting even begins.
Understanding the friction between compute availability, memory bandwidth, and data size is what separates a fragile prototype from a resilient product. The hardware imposes strict rules, and mastering these optimizations allows you to operate at the very edge of those physical limits.
But as you sit there at your desk with your IDE and your infrastructure, I want to leave you with one final thought to mull over.
Okay.
We talked about how brilliant speculative decoding is. A tiny draft model guessing what the big model will say, delivering a massive speed up.
Right.
But what happens when your users start asking highly complex, totally unprecedented, incredibly nuanced questions? The kind of questions a small intern model has absolutely no chance of predicting correctly. Does that clever intern suddenly get every single draft wrong, forcing the senior engineer to reject the entire sequence and rewrite everything from scratch anyway?
That's a real risk.
And if so, does that magical 3x speedup suddenly vanish right when your system is under the most pressure,
Well,
dealing with the hardest problems? It's something to think about the next time you are staring at a latency graph, wondering why your production system just ground to a halt. Good luck with the deployment.